All right, guys, before we have our quiz over static electricity, there's one more concept that I want to go over with you, and it's something called Coulomb's law, Coulomb, Coulomb, and it was named after a man named Coulomb, and it's Coulomb's law. And basically, we're going to talk about electric force, and I'm going to play this short little clip, which is similar to a demo that we did in class.
Hi there. Today I'm going to show you a fun little static electricity experiment, and all we've got are some little bits of paper. They've come out of a hole punch, those little circles of paper, and we've got a comb. So what we want to do now is comb that comb through my hair. Okay, there we go. Just combing the comb through my hair. Let's see what happens when we put it near the bits of paper. Woohoo! They all start jumping around and attach themselves to the comb. Okay, so there we go. The static electricity built up on the comb attracts the bits of paper, and they stick to the comb.
All right, so I'm going to go to this next slide for you. All right, so think back to when we studied force, which was not that long ago. And what did we say the definition of a force is? Well, the Reader's Digest version is that a force is either a push or a pull, right? Well, when we rubbed that balloon with the piece of wool in the classroom, the balloon became charged, remember? And I held the balloon over the little bits of paper, and the paper jumped up to the balloon. So it was a pull, right? The paper was pulled up to the balloon. All right, so that is what we call an electric force. It was a pull on the paper bits to raise them off the table. So that is an electric force. And it occurs even when the balloon is held away from the paper bits. In other words, we've always talked about a force where you literally had to push something with your hand, or pull something, maybe with a rope. Well, this is a force that works without touching, all right? And we're going to talk about what that's called in just a second. All right, so let's answer this question. If a charged balloon is held above some small bits of paper, a blank is exerted upon the paper from the balloon. What is that going to be? An electric force, a gravitational force, a frictional force, or a normal force? Y'all answer. Okay, so like all forces, an electrical force is either a push or a pull exerted upon an object. This is what we call a non-contact force, meaning that it does not have to literally touch the other object. One object will push or pull on another object without actually having to touch that object. So true or false? An electrical force is a push or a pull. Is that true or false? A non-contact force is which of these? A force that exists from two objects rubbing against each other, a force that exists from kicking a soccer ball, a force that exists over a separation distance, or a force that exists from gases coming out the back of a rocket. Okay, so let's talk about what factors affect how strong the force is. In other words, we would call that, Sophie, no. We would call that the magnitude of the force, okay? Well, there are three factors that affect how strong or how big the force is between two charged objects. They are the amount of the charge of the first object, the amount of the charge of the second object, and how far apart those two objects are. Okay, so in the case of the balloon, it would have been the amount of charge that I had on the balloon, if we were trying to attract the paper, it would be the amount of charge on the paper, and then how far the balloon was from the paper. How many factors affect the magnitude of an electrical force? Did I say it was one factor, two factors, three factors, or four factors that affect the magnitude of a force, of an electrical force? All right, the factors that affect the magnitude of an electrical force are the charges of the objects and the masses of the objects, the charges of the objects and the distance between them, the mass of the objects and the distance between them, the mass of the objects, and the velocity of the objects. If you don't know the answer to these, just go back and rewatch that portion of the video. All right, so I'm going to stop the video right here, and then I'm going to switch to my whiteboard and show you guys some a formula. Okay, in the formula though, you're gonna see a Q1, a Q2, and an R, and I'm going to explain what those are. Okay guys, so I left off the other portion of the video talking about Coulomb's law, okay? And what Coulomb's law is talking about is the amount or magnitude of the electrical force, okay? So electrical force. And there's a formula for that, of course. And K is known as Coulomb's constant, okay? So it's just a constant. You're not going to need to know it. And it's the constant times Q1, which is the amount of charge on your first object. So maybe the balloon, first object. Okay, multiplied times Q2, which, as you might guess, is the charge, the amount of charge on the second object, such as the paper. Okay, you're going to multiply the charge of the first object times the charge of the second object, and that's all going to be divided by, you'll either see it as R, or you might see it as, let's see if I can erase this without my finger. You'll either see it as R, or you'll see it as D. I've seen it both ways. R stands for radius, and of course D just stands for distance. And D really is a little bit more appropriate for us because we're talking about the distance between these two objects, all right? So are you guys going to have to solve for these? No, you're not, but let me tell you what you are going to need to do. You're going to need to know the relationship between the distance and the charges on the amount of force, okay? How this relationship affects the amount of force. What do I mean by that? Well, basically, remember when I charged the balloon and I rubbed it on my hair and I held it above the paper, okay? So I'm gonna draw a little balloon here, okay? Pretty bad looking balloon, and some little bits of paper here on the table, okay? I rubbed the balloon on my hair and induced a positive charge, meaning I stripped electrons from the balloon onto my hair or onto the wool, okay? So I gave the balloon a positive charge, okay? And then I held it near the paper bits, and then the paper bits, the electrons that were in the teeny tiny little pieces of paper came to the very surface of the paper. Think about the doorknob and the wall activity from yesterday. And the protons were left at the surface, all right? And I'm sorry, the electrons came to the surface and there was an attraction, all right? And those papers jumped up towards the balloon, all right? But think about it. When I held the balloon way up high, the paper didn't jump until I brought the balloon fairly close, all right? So essentially, the closer the objects are, the stronger the force is going to be. Okay, so that's one factor that affects the stronger the force. That's one factor that affects the amount of force, okay, is the distance. All right. The other, as you might imagine, is the amount of charge, Q1. So this is going to be the distance. Q1 is going to be if I rub that balloon on my hair just a little, I may not give it much charge. Okay, but if I rub it a lot, I'm going to give it more charge. So the more charge something has, more charge, the greater the force again. So with Q1, the greater the force, the greater the charge, the greater the force. Same thing with the paper. So we'll call that Q2. Same thing. The greater the charge, so the more charge on the paper, the greater the force as well. Okay? So that if you double the distance between these two objects, you're going to half the amount of the force. Okay? So basically, you guys just need to understand that as you bring two charged objects closer and closer and closer and closer, the force gets stronger and stronger and stronger. As the charges increase, the force also increases. And that's Coulomb's law.